An X-ray is a way of taking pictures of the inside of your body using a special machine that sends out invisible rays. These rays can pass through most things, but some things like bones and metal can stop them. When the rays hit a special detector or a film, they make an image that shows the shadows of the things inside your body. The image is called an X-ray or a radiograph. Why do we need X-rays? X-rays are very useful for doctors and other health professionals because they can help them see what is going on inside your body without cutting you open. For example, X-rays can help them find out if you have a broken bone or a foreign object in your body. Check if you have an infection in your lungs or a tumor in your organs. Measure the size and shape of your heart and blood vessels. Plan a surgery or a treatment. Monitor how well a treatment is working. How do X-rays work? To get an X-ray, you need to go to a special room where there is an X-ray machine. The machine has two parts, a source that makes the X-rays and a detector that captures them. The source and the detector are on opposite sides of the room. The person who operates the machine is called a radiographer or a radiologic technologist. They will ask you to lie down on a table or stand in front of a board. They will also ask you to remove any clothing or jewelry that might interfere with the X-ray. They might give you a gown to wear or cover you with a sheet. The radiographer will then position you in the machine so that the part of your body that needs to be X-rayed is between the source and the detector. They might use pillows, straps, or sandbags to keep you still and comfortable. They might also place a shield over some parts of your body that don't need to be X-rayed to protect them from radiation. The radiographer will then go behind a window or a wall where they can see you and control the machine. They will ask you to hold your breath and stay still for a few seconds while they take the picture. You might hear a buzzing sound when the machine is on. You won't feel anything when the X-rays pass through your body. The radiographer might take more than one picture from different angles to get a better view of your body. The whole process usually takes only a few minutes. How do we read X-rays? After taking the pictures, the radiographer will send them to a computer or print them on film. Then, another person called a radiologist will look at them and write a report. A radiologist is a doctor who specializes in reading X-rays and other imaging tests. The radiologist will use a methodical approach to read the X-rays and look for any abnormalities or signs of disease. They will look at things like the quality of the image, if it is clear, bright, and well positioned. The airway, if the trachea, the tube that carries air to your lungs, is in the middle or deviated to one side. The breathing, if the lungs are clear, inflated, and symmetrical. The cardiac, if the heart is normal in size, shape, and position. The diaphragm, if the muscle that separates your chest from your abdomen is curved and smooth. Everything else, if there are any changes in the bones, soft tissues, mediastinum, the space between your lungs, or other structures. The radiologist will compare your X-rays with previous ones if you have any and with normal ones for people of your age and gender. They will also consider your medical history and symptoms. They will then write down their findings and conclusions in a report that they will send to your doctor. Your doctor will explain to you what the report means and what you need to do next. Sometimes, you might need more tests or treatments based on the results of your X-ray. Are there any risks? X-rays are generally safe and have many benefits for diagnosing and treating diseases. However, they also have some risks that you should be aware of. One risk is radiation exposure. Radiation is energy that travels in waves or particles and can damage cells in your body. Too much radiation can cause cancer or other health problems. The amount of radiation you get from an X-ray is very small and usually not harmful. It is similar to the amount you get from natural sources, such as the sun or the soil, in a few days or weeks. However, the risk can add up over time if you have many X-rays or other imaging tests that use radiation. Another risk is allergic reaction. Some people might be allergic to the contrast dye that is sometimes used to make certain parts of your body show up better on the X-ray. The contrast dye is a liquid that you drink or get injected into your vein before the X-ray. It can cause itching, hives, nausea, vomiting, or difficulty breathing in some people. To reduce these risks, you should tell your doctor and the radiographer if you are pregnant or might be pregnant, as radiation can harm your unborn baby. Tell your doctor and the radiographer if you have any allergies or medical conditions that might affect the X-ray. Follow the instructions of the radiographer before, during, and after the X-ray. Ask your doctor if you have any questions or concerns about the X-ray. An X-ray is a medical imaging technique that uses invisible rays to create pictures of the inside of your body. It can help doctors diagnose and treat diseases. It is usually quick and painless, but it also has some risks that you should know about. You should always talk to your doctor before and after getting an X-ray to understand what it means for your health. Here are some details about several scientists related to X-ray technology and their impact. Wilhelm Röntgen. He was the German physicist who discovered X-rays in 1895 while experimenting with electron beams in a gas discharge tube. He noticed that a fluorescent screen in his lab started to glow when the electron beam was turned on. He also observed that the X-rays could penetrate through various materials and produce images of their internal structures. He was the first to take an X-ray image of a human body part, his wife's hand. He received the first Nobel Prize in Physics in 1901 for his discovery. Max von Laue. He was a German physicist who discovered the diffraction of X-rays by crystals in 1912. He proposed that crystals could act as natural gratings for X-rays and produce interference patterns that reveal their atomic structure. He used a copper sulfate crystal and an X-ray tube to demonstrate his idea. He received the Nobel Prize in Physics in 1914 for his discovery. William Henry Bragg and William Lawrence Bragg. They were a father and son team of British physicists who developed the Bragg's law of X-ray diffraction in 1913. They showed that the angle of reflection of X-rays by a crystal depends on the wavelength of the X-rays and the spacing of the crystal planes. They used this law to determine the structures of various crystals, such as sodium chloride, diamond, and zinc sulfide. They shared the Nobel Prize in Physics in 1915 for their work. Charles Glover Barkla. He was a British physicist who discovered the characteristic X-rays of elements in 1909. He found that when X-rays are scattered by a material, they produce secondary X-rays with specific wavelengths that depend on the atomic number of the material. He also showed that these characteristic X-rays can be used to identify elements and measure their concentrations. He received the Nobel Prize in Physics in 1917 for his discovery. Arthur Holly Compton. He was an American physicist who discovered the Compton effect in 1923. He showed that when X-rays collide with electrons, they lose some of their energy and change their wavelength. This phenomenon demonstrates that X-rays have both wave and particle properties, and supports the quantum theory of light. He received the Nobel Prize in Physics in 1927 for his discovery. Latest research findings about X-ray technology. X-ray technology is a field that is constantly evolving and improving, thanks to the efforts of scientists and engineers around the world. X-rays are a type of electromagnetic radiation that can penetrate through various materials and reveal their internal structure. They have many applications in medicine, industry, security, and science. Here are some of the recent research findings about X-ray technology that are worth noting. Self-wavelength shifting in two-dimensional perovskite for sensitive and fast gamma-ray detection. Gamma rays are high-energy X-rays that can be used for imaging and detecting nuclear materials, but they require efficient and fast scintillators to convert them into visible light. A team of researchers from China and Japan have developed a new type of scintillator based on two-dimensional perovskite materials that can shift the wavelength of gamma rays to match the sensitivity of silicon photodetectors. This improves the light output and the response time of the scintillator, making it suitable for high-resolution and high-speed gamma-ray imaging. Apochromatic X-ray focusing. X-ray microscopy is a technique that can achieve nanometer-scale resolution and contrast by using X-rays to image tiny structures. However, one of the challenges of X-ray microscopy is chromatic aberration, which means that different wavelengths of X-rays are focused at different points, resulting in blurred images. A group of researchers from Switzerland and Germany have designed and demonstrated a new type of X-ray lens that can correct chromatic aberration and achieve apochromatic focusing too. This means that the lens can focus X-rays of different wavelengths at the same point, enhancing the image quality and resolution. A sensitive high-repetition rate arrival time monitor for X-ray free electron lasers. X-ray free electron lasers, XFELs, are powerful sources of ultra-fast and coherent X-rays that can be used for studying ultra-fast phenomena and atomic scale dynamics. However, to perform time-resolve experiments with XFELs, it is essential to know the exact arrival time of the X-ray pulses with high precision and accuracy. A team of researchers from Germany and Sweden have developed a new device that can measure the arrival time of XFEL pulses with sub-femtosecond resolution and stability. 3. The device uses a gas jet target and an electro-optic sampling technique to detect the temporal overlap between the XFEL pulse and an optical laser pulse. Comparing X-ray phase contrast imaging using a Talbot array illuminator to propagation-based imaging for non-homogeneous biomedical samples. X-ray phase contrast imaging is a technique that can enhance the contrast and visibility of low-density or low atomic number materials that are otherwise hard to see with conventional X-ray imaging. There are different methods to achieve phase contrast imaging, such as propagation-based imaging, PBI, and Torbit Array Illuminator, TI. A team of researchers from Germany have compared these two methods for imaging non-homogeneous biomedical samples, such as tissue phantoms, mouse organs, and human teeth. They found that TI offers better contrast to noise ratio and edge enhancement than PBI, but PBI has higher spatial resolution and less artifacts than TI. Direct high-resolution X-ray imaging exploiting pseudorandomness. X-ray imaging usually requires a collimated or coherent source of X-rays and a detector with high spatial resolution. However, these requirements are often difficult or expensive to meet in practice. A team of researchers from South Korea have proposed a new method for X-ray imaging that can overcome these limitations by exploiting pseudorandomness. The method uses a pseudorandom binary mask to modulate the X-rays from an incoherent source and then applies a computational algorithm to reconstruct the high-resolution image from the low-resolution measurements. Time-domain double-slit interference of electron produced by XUV synchrotron radiation. The double-slit experiment is a classic demonstration of quantum mechanics, where a beam of particles or waves passing through two slits produces an interference pattern on a screen. However, performing this experiment with electrons is challenging because they interact strongly with each other and with external fields. A team of researchers from Japan have successfully performed a time-domain double-slit interference experiment with electrons produced by extreme ultraviolet, XUV, synchrotron radiation. They used a streak camera to measure the arrival time distribution of the electrons on the screen and observed quantum interference fringes in time domain. Direct high-resolution X-ray imaging exploiting pseudorandomness. X-ray imaging usually requires a collimated or coherent source of X-rays and a detector with high spatial resolution. However, these requirements are often difficult or expensive to meet in practice. A team of researchers from South Korea have proposed a new method for X-ray imaging that can overcome these limitations by exploiting pseudorandomness. They used a pseudorandom phase mask to modulate the incident X-rays and create a speckle pattern on the detector. Then, they applied a mathematical algorithm to reconstruct the high-resolution image of the sample from the speckle pattern. They demonstrated that this method can achieve sub-micrometer resolution and high contrast with a simple setup and a single-shot measurement. Time-domain double-slit interference of electron produced by XUV synchrotron radiation. The double-slit experiment is a classic demonstration of quantum mechanics, where a beam of particles or waves passing through two slits produces an interference pattern on a screen. However, performing this experiment with electrons is challenging because they are easily affected by external fields and interactions. A team of researchers from Japan have performed a time-domain double-slit experiment with electrons produced by extreme ultraviolet, XUV, synchrotron radiation. They used a thin metal foil as the double slit and measured the time of flight spectra of the transmitted electrons. They observed an interference pattern that depended on the energy and angle of the incident XUV photons, revealing the quantum nature of the electron emission process. Tunable quantum recoil lasing in plasmas. Quantum recoil lasing, QRL, is a phenomenon where an intense laser pulse interacts with a plasma and generates coherent X-rays through stimulated Raman scattering. The frequency of the X-rays depends on the recoil energy of the plasma electrons that scatter the laser photons. A team of researchers from China and France have demonstrated a tunable QRL in plasmas by controlling the laser polarization and intensity. They showed that by changing the polarization from linear to circular, they could tune the X-ray frequency from 1.5 keV to 2.5 keV. They also showed that by increasing the laser intensity, they could enhance the X-ray brightness by 2 orders of magnitude.